Okay, in this video I'd like to walk through another application question from our homework number 9. This one happens to be number 7 in the set, and it involves what we call Newton's law of heating or cooling. And here again, if you use the question help in Math Excel, they lead you towards this style of equation, which is fine. You can use that reference and learn a lot from it. However, it's not consistent with the format that I use in my other videos. And so in this video I'd like to just again reiterate how you can use either method, and I'd also like to talk a little bit about questions B, C, and D, where we use the features of our calculator to investigate a bit further. So at the heart of this question we're being asked how long does it take for this pizza that we're pulling out of the oven to cool to 130 degrees Fahrenheit. Evidently that's when it's going to be safe to eat. So the pizza's been in the oven for a certain amount of time. We don't know, and that doesn't matter, but it is 400 degrees currently. The pizza is 400 degrees. It's taken out of the oven at 9 o'clock p.m. That's going to be helpful to answer this question down here, but otherwise it's irrelevant. The room temperature is a constant 72 degrees, and we know that there's a data point that's been collected. After 5 minutes, the pizza is already cooled to 300 degrees. Now, one thing I want to point out is that in most situations, in most of our exponential growth or decay models so far, we've had exponential functions, especially in a cooling scenario. They start at some value and they drop and they tend towards 0. They'll level off here. The rest of this graph would race off towards infinity to the left. But this graph is tending towards 0. What we've got to remind ourselves of in these Newton's law problems of heating and cooling, we're not tending towards 0. In fact, we're leveling off towards some other ambient temperature. And so room temperature in this particular example is 72 degrees, which may be this line here. And as the pizza comes out of the oven, if it's 400 degrees, it might tend towards this asymptote and level off. And that's the temperature that it's going to settle at. And this offset, this vertical offset, has to be accounted for in all of our examples. Now, in Math Excel, that vertical offset is going to be labeled as T, capital T. That's our ambient air temperature. And in the format that I've been using with this exponential growth equation, that number is represented by the letter B. T or B. So the first thing I'm going to do is just talk through the Math Excel layout for a second, and then we'll talk a little bit more about how I would use my format. So a little bit about this equation. I'm not entirely certain where the letter U comes from. Perhaps it was mentioned and I didn't pay close enough attention to it, but U does essentially represent our ultimate or ending temperature based on some amount of time, lowercase t, that's passed. So this U subscript 0, U sub 0, or sometimes called U naught, naught meaning 0. U naught is our starting temperature, so what the temperature of the pizza is as it's pulled from the oven. Capital T is our ambient air temperature. What's the temperature that the pizza is going to be approaching as time passes? K, this value here in the exponent, is a coefficient times lowercase t for time, but this K value indicates our growth or decay rate. We've seen that in several examples prior. And then finally, lowercase t, this is our independent variable. And this is our independent variable. This is the value that we're going to be solving for. And this lowercase t stands for time. And in this case, we're talking about time in minutes. And we recognize that we're talking about time in minutes because, well, that's pretty much what the data has been presented as. So as I read through the problem, I understand what U naught is. That's 400 degrees. That's the temperature of the pizza as it comes out of the oven. Capital T, the temperature of the room, is 72 degrees. And then the the ultimate temperature or the ending temperature after 5 minutes, if we were to stop our experiment and measure the temperature of the pizza after 5 minutes, is 300 degrees. Now this data point's important because with this data point here, we can now substitute a lowercase t value and a temperature, an ultimate temperature value, into an equation, or into the equation. And with our substitutions, we can now establish our K value, the growth or decay rate in this case. So I noted that U5 is equal to 300, so U of 5 is 300. I've made that replacement in the second line. But in the first line, I've replaced capital T with 72 here and here. I replaced a U0 with 400 because that was our starting temperature. And I replaced lowercase t with 5 because that's the amount of time that's passed. And after I make my second substitution, the 300 degree number representing U5, in this line down below, now I'm set up to solve for the unknown variable K. Now one thing to keep in mind, and I don't think I caught it with my screen capture before, is that questions like Part A ask us to solve for this time, but they don't want us to round at all until the very final answer. And what I like to do then is I like to do all of my math by hand, written on paper, and I don't reach for the calculator at all. I don't even do any mental math along the way. Certainly you could perform some of the operations, some of the arithmetic along the way. You could even use a calculator if you wanted to, but I stay away from that because I don't want the calculator to produce a result that I end up having to round. I don't want to lose any accuracy along the way. So rather than sometimes use the calculator and sometimes not use the calculator, and also to avoid, the concerns of rounding or obtaining a non-precise result, I just avoid that altogether, and I simply do the math without a calculator, and then I use the calculator one time at the very end. Now, with 300 that equals the rest of this equation, two things have to happen first. We need to start isolating the exponential. What we need is some sort of base raised to an exponent. And to make that happen, I'm going to subtract 72 to the left side of the equation, and then I have to divide by whatever 400 minus 72 is. Again, I don't bother simplifying that. That doesn't help me out in this particular case. So we subtracted 72 and we divided by 400 minus 72, and that's where this expression comes from. Now that we have some base raised to an exponential power here, I could rewrite this exponential as a logarithm. The logarithm requires the same base as the exponent, so that logarithm is the natural logarithm. This ln notation, if you recall, is the same as a logarithm with a base of e. It's just one of those special examples. So we've got the logarithm evaluated at this target that we just identified a moment ago, this argument we call that. And if the logarithm of that number is equal to 5k, then the very last thing that we have to do is divide by 5, and we'd have our k value. Now, this result has been obtained without the use of a calculator, and for our purposes in this problem, I'm going to leave that as it is, and I'm still not going to reach for the calculator yet. If you wanted to, you could find what that number was. We could go to the calculator now and obtain the result, but I still wouldn't do that because we haven't answered the question that's been posed to us. We haven't found the time or how much time it takes for this pizza to cool to 130 degrees. So in all honesty, I like to leave this k value as it is in this particular form because there's been no rounding and the answer is precise. Well, now that we know the k value and we know our ultimate temperature, our ending temperature is going to be 132 degrees. The starting temperature was still 72. The ambient temperature was still 72, and the starting temperature is still 400. So all of this data has been given to us already. The difference this time is we now know our k value in the form of this complex fraction, And our goal is to solve for t, to isolate t. Well, t is sitting in the exponent, and when we solve for a variable or an unknown in an exponent, we have to use a logarithm. In order to make that work, in order for us to solve for that logarithm, we need to isolate this exponential. So again, we're starting with 130, and we'll subtract 72 to move it to the left-hand side. We'll divide by 400 minus 72, and that moves it to the left-hand side. And again, we've produced a similar-looking expression here. We have an exponential with a base of e. It's raised to a power that contains a variable. So in order to solve for this variable, we'll rewrite the exponential as a logarithm. Again, the natural log notation, ln, this is an L, not an I. ln is equal to a logarithm with a base of e. Since the base of our exponent was e, the base of our logarithm has to be e. We don't show that letter e because natural logarithm implies the letter e. So anyway, we've got this natural logarithm on the left, which helped us isolate the exponent, which is our k value times t. And then lastly, to isolate t, we needed to divide, and this is where it gets pretty interesting. We needed to divide this logarithm on the left by this logarithm on the right. And certainly we could use some log properties to combine these two. We've seen that in the past. But in all actuality, since we're going to be reaching for a calculator in a moment anyway, I don't find that it's particularly necessary to use the log laws here. So anyway, t, when isolated, ends up being the logarithm from the left side of the equation divided by the logarithm from the right side of the equation. And when I finally reach for and execute this expression in the calculator, I ended up with a result t equaled 23.82 minutes. Now, we removed the pizza at 9 p.m., and when we add to that, and I was looking at the drop-down menu a minute ago, they're whole number minutes. So when we add to that 24 minutes, then the pizza will be safe to eat at 9:24 p.m., and that's the solution that we would select for this Math Excel problem. Again, you'll notice that on this problem, there were no checkpoints along the way. We didn't have to identify a k value in Math Excel. We didn't have to identify the subscript values for U naught or capital T or any of that information. So because of that, we don't have to rely on this particular equation to solve this problem. We can use what I would consider a more simple form that we addressed on the left side over here. Now it's a bit more simple because it has fewer parts, but there is one change that we've got to be aware of that makes it slightly different than the examples we've seen in the past. This C value, our initial value, is no longer the measurement above the horizontal axis. We got so used to measuring C as simply being the coordinate position right here on the y-axis because that C value measures the height of this logarithm, or I'm sorry, of this exponential above starting, or above baseline, I should say. That C value at this particular coordinate is only good if the graph tends towards 0, if it levels off at the x-axis. Since the Newton's law problems do not level off towards the x-axis, instead they level off towards some room temperature, some offset value. The C value in this case is not the measurement from the point to the x-axis, but it's the distance from that point to this horizontal line. And so we'll just note here that the initial value C is the initial value or amount above or below the air temperature. So when we're dealing with a Newton's law of heating problem, we see the same thing. We'll see this graph tend towards the air temperature, and the B value could be, I'm sorry, the C value could be this measurement down beneath that horizontal asymptote. So if we identify our variables this way, we can again solve for x this time instead of t for time. Now, unlike the examples from Math Excel, I do think it's worthwhile to compute the C value. The math is the same as what we saw prior. In fact, this U naught and T, when we subtract them, that is the same as our C value in our other format. The starting temperature minus the air temperature is the same as this starting temperature minus air temperature. And that number 328 is going to be used in place of C instead of the parenthesis group that we had over here. So the big difference with this is that to identify our growth factor, instead of using a logarithm, we're actually going to use a radical sign. Similar to before, I'm entering the temperature after 5 minutes on the left side of the equation, our C value, which we quickly computed a moment ago, our time value 5, and our air temperature 72. This time the value that we're solving for is a, which is the base of an exponent, not an exponential. I'm sorry, the base of an exponential, not the exponent itself. And when we solve for the base, we end up using radicals to make that happen. So we subtracted the 72 to move it to the left-hand side. We divided by 328 to move it to the left-hand side. And now we're left with a to the power of 5 that equals this expression. Well, to undo an exponent that equals 5, to undo this power, we would use the fifth root, or a radical with an index of 5. And the fifth root of this fraction that we established on the left will represent our growth factor. Here again, if you wanted to, you could compute the A value. You could identify what that is, but I'm not going to because I don't want to risk losing accuracy by rounding this result. Instead, we'll go back to the format. We've got our target temperature of 130 degrees, our C value, initial temperature above air temp at 328, our air temperature is 72, and our A value of the fifth root of this fraction. Now we can do the math to isolate x. This time around, since x is sitting in the exponent, we will use a logarithm in order to isolate x. But the first thing we must do, as we've done in the past, is subtract 72 to move it to the left side, divide by 328 to move that to the left side, and now we've got an exponential with a base and an exponent only, for which we can rewrite as a logarithm. The logarithm in this line must use the same base as the exponential in the line above. So the logarithm's base is the fifth root of the fraction. The argument, or the value that we're applying the logarithm against, is the result from the exponent in the line before. And after rewriting the exponential as a logarithm, we now have an opportunity to solve for x. And here again, the time in minutes ended up being 23.8208 coming off of my calculator. That was the same result that we saw a minute ago. And here again, when adding that to the 9 o'clock start time, we see that our pizza is ready at 9:24 p.m. I did confirm this result with Math Excel, and they did accept that as the answer. I did that off screen, actually on a separate computer, so I can't show that here. So that was a long discussion, but again, I think it's a fair point to make when comparing the two techniques. I'll let you decide which one you feel more comfortable with when you take the test in a couple weeks. So let's try to finish out this video by addressing B, C, and D. Part B, use a graphing utility to graph the relationship between temperature and time. So that's our fancy way of just simply asking us to graph this equation. Now, it's no secret I'm a bit more comfortable and a bit biased to the layout on the left, so this is the one that I'm going to graph. It's not real clear what the equation is going to look like when I bring it to the calculator, so let me rewrite it here. The equation is going to be f of x equals 328 times the fifth root of, let me double check that again before I commit to it, 300 minus 72 divided by 328 to the power of x plus 72. Sorry, I didn't mean to run out of room there. But this is the expression, this is the equation that I'd like to graph. Again, I'm not going to simplify this a value. I'll let the calculator do all of that work. But the function is built on x, which is time, and x has to be our independent variable in this layout. So when I go to the calculator, again, I always like to press the on button until we get to this home screen, and then I'll choose number 1 for a new document. I'm going to go straight to a graphs page, so I'll press number 2. And here's my opportunity to write the equation. 328 times the 5th root of a fraction, so I'll press Control Divide to create that fraction. 300 minus 72 over 328. We'll jump to the outside of the grouping symbol here and create the exponent of 5. Oops, sorry, not 5. We want to use x this time. This way we'll create a graph based on many different times. And to that we'll add 72. Now we don't see anything here, but that doesn't mean that nothing happened. Let's keep in mind that in our last example it took 24 minutes until the pizza's temperature dropped to 300 degrees. So, sorry, until it dropped to 130 degrees. So if we're thinking about this graph, this quick sketch, the sketch that we had over here on the left-hand side, a couple things we know right now, and I'm going to use some different colors to make this stand out, hopefully. At time 0, the temperature was 400, and at time 24, the temperature was 130 degrees. So what we need to do is we need to create a window on our calculator that's going to capture those two data points. And then there's also another one here at 5 minutes. We had a temperature of 300, but if we can capture the first and the last data point, then that one in the middle should be accounted for as well. So let's set up a window that'll make that happen. I think I'd like to go from, say, -3 to +30 on the x-axis. So we'll go to our menu button and choose Window Zoom and adjust our window settings. Again, out of habit, I like to make the x minimum about 10% less than 0. 10% of my right side, I should say, less than 0. So if I'm going up to 30 on the right, then I'm going to go down 3. 3 is 10% of this. I'm going to go down 3 or move left 3 on the x-axis. This will allow the y-axis to remain visible on our graph. Now I could just graph this and let the calculator fit the window, but I'm going to manually set the y scale this time. So for the y minimum, I'm going to set it at -45 and the y maximum to be 450. Again, with my 10% reference here, I know that the temperature has to be above 400 degrees in order to see the entire graph. So I'm going to let the maximum temperature be 450. 10% of 450 is 45, so I want to display 45 units below the x-axis along the y-axis. That 10% extra scaling allows me to see the x and y-axis. If I had started at 0 on x or 0 on the y-axis, then these axes will be right against the window, and that makes it, to me, a little bit harder to view and interpret. So I'm just going to click and drag this equation out of the way so that we can see a little bit more of the graph. And here's our temperature relative to time. As temperature increases, as time increases, time was our x-axis and temperature was our y-axis. As time increases, the temperature decreases, and it follows this curve. It's not a linear decay at all. And on Math Excel, when you answer this question, I'm certain that you'll be presented with several different graphs to look at, and you'll have to decide which one's the best fit. So one thing to pay close attention to when answering questions on Part B is the scaling. Look at the x and y axis to view the scaling options as well as the window size. That'll help you decide which one to choose. Now for Part C, use the intersect to determine the time when the pizza reaches 160 degrees. So maybe somebody with higher pain tolerance likes their pizza to be a little bit warmer at 160 degrees. Rather than set up the equation and solve for that again, which really wouldn't be all that hard, if you've got this expression in your calculator, all you've got to do is change 130 to 160 and you'll be done. Same thing with this format over here. If you change 130 to 160, you can re-execute that expression. But to show you another way to solve this, let's go ahead and use our calculator. There's a horizontal line at 160 degrees. We'll call that our target line. We want to know, when does the temperature graph reach our target line? Well, we can enter that second equation by pressing the tab key. This will bring up your function bar, and we'll simply type 160. So our second function is equal to 160. With y equals 160, we now have this horizontal line, and this point of intersection is where the temperature on the blue graph reaches 160 degrees, the red graph. We've seen this in the past, the intersection option, but I'll remind you again that when you press Menu and choose option 6 to analyze the graph, then option number 4 presents itself as the intersection of two equations. With our mouse, we'll have to click a position somewhere to the left of where that intersection occurs. This gives us a lower boundary. Then drag to the right to find where the intersection occurs. We have to pick a point to the right side to identify an upper boundary. And now we have a solution. We know that at time 18.089, the temperature will be 160 degrees. Now, your calculator may display an appropriate number of decimals based on what Math Excel is requesting. If for some reason it doesn't, you can jump into the menu, choose option 9 for settings, and adjust your display digits. If Math Excel requires you to show 4 decimal places, then I would suggest going down to the bottom of the list and choose Fix 4. This will force every coordinate to show 4 decimal points. Now, that's a bit annoying because even these answers here that are precise at a whole number, they'll show 4 decimal points as well, but at least you're guaranteed to see the 4 decimals for the value that you might be after. Most of the time, however, what I would suggest is to leave your calculator on auto or float. I'm going to switch mine back to float, and this will show usually more decimals than necessary. In this particular case, the calculator has decided just to show us 3. So at least we now have a solution for part C. We know that it's 18 minutes after it's removed from the oven, so at 9:18 p.m. the pizza would be ready if you wanted to eat it at 160 degrees. Now for part D, just as an example to see what happens when we start investigating larger values of time, what do you notice about the temperature? So we'll jump into the menu option and choose Trace, and then we'll select number 1, Graph Trace. Now the calculator, I think, defaults to function number 1, which is good for us, but if for some reason you wanted to trace this red graph, all you have to do is press the up or down arrow, and the calculator will switch between the two. Now, it shouldn't be a rapid switch like mine's doing. I think that's an error on my computer here because I'm using a stylus on the screen. But you'll be able to manually select one or the other. I'm going to stay on the blue graph here just to trace. And so now I'm just going to click this right arrow, and I can then kind of investigate what's happening to the y values as x increases. And there should be no surprise here. As time increases, the temperature decreases. And as we said before, this temperature is going to decrease and tend towards air temperature. So we should see it leveling off towards 72. Now for extremely large values, let's say we wanted to let this thing sit out for 2 hours, 120 minutes. I don't think we're going to sit here and tap the right-hand arrow for that many times until we reach 120. The nice thing about these TI calculators is that if I simply type 120 while the trace command is active, if I just type 120 and press enter, then the calculator is going to run its result out to an x value of 120, and it's going to display the y value associated with it. If we jump out to 360, 6 hours after we remove the pizza, well, now we can see that the temperature is approximately 72 degrees. So here's the final question that I'll leave you with to think about. Is the temperature of that pizza really 72 degrees according to this model? Or is it slightly different than 72 degrees? Think about it, and if you're unsure, ask me next time we see each other in class, or send me a message and we can chat about it. That's all that I have for this video. I know it got quite lengthy there, but I think you'll benefit from seeing both approaches to solving this problem, as well as some more practice with the calculator. If you've got further questions, please let me know. Otherwise, thanks for watching.